Okay, calculus. It's used in electronics, and electrical engineers have to know it so they can calculate pretty much anything they need related to their projects. And capacitors and inductors are two of the major components used in pretty much every electronic device on the market. And understanding their purpose and how to calculate the values in relation to them that are needed to run the item the right way is imperative in order to design something that's going to work right all the time, or as often as possible. Alright, here we have 4 different equations related to the different items you see here. This is the symbol for capacitance, or capacitor. One of the symbols, there's several different variations of it. And over here we have the symbol for inductor, and that's just one of the variations of that. And over here I've made some notes here. We have I, which is also the symbol for, or character for amp, V for voltage, and T for time. Now the dV over dt, that is taking the derivative of those values, or the equation related to those values. And then the C here is just a constant related to the particular capacitor. And same thing over here, L, that is a constant related to inductors, or the particular inductor used. And then down here we have the equation for integration to get back to other values, to get your voltage. And again here, C is a constant, I is amps, T in time. And if you'll notice, if you look across either side, you'll notice the fact that the equations are kind of similar to each other, and they relate to each other quite a bit. Over here you'll notice that we have voltage equals I times R. R here is also resistance or ohms. Terms are interchangeable there. And what we're going to discuss here is capacitors, and the fact that after a device is turned off, you don't need that capacitor storing power, so you have to have a way to discharge it. A common way is to hook in an inline resistor or a parallel resistor with the capacitor, so that way it discharges the capacitor over enough time so that way you don't have to worry about frying any components. We can rewrite that same equation for voltage to give us amps, and then we can go over here and look at the other side of the equation that we're going to be incorporating together to make a simpler equation. Q, which is the charge of that capacitor, and that's related to the constant times the voltage. And we can rewrite that again as voltage equals Q over C. If we incorporate that into our equation over here and replace V with Q over C, we come down and we have a new equation of I equals Q over RC. And that's just simple algebra skills there. And where RC here is actually a time constant, which we'll discuss a little bit later on. And in order to discharge a capacitor, obviously you're dropping the power in that capacitor, and that is why I've written a negative over here, because we're dropping the power. And this is going to give us how long it's going to take to get to the given value to discharge that capacitor. And there's typically a time frame in most capacitors and electronics that you want to aim for. It just varies the type of electronic that your electronic device that you're using. So what we're going to do is we're actually going to end up integrating both sides of the formula, but in the meantime we're actually going to just manipulate the equation to where we can end up with this equation over here. And this is a simplified equation that just makes it easier to deal with. Now over here I've rewritten the same equation, Okay, this is the original information, and we've written it down here. I'm just going to leave the integrand symbols in there because it doesn't matter at this point. We can worry about that at the end. So first off, what we start off doing is just multiplying this side by dt. We do it to this side, so that means we have to do it over here as well. And then that means we end up with this equation. Simplify this equation down, and we end up with this one over here. Obviously, we lose the dt on this side. Alright, and keep going again. Now we're going to move the q over. Divide by q, it cancels out on the left side. Well, divide by q on this side, well, q ends up being just 1 over q. And we're keeping that because of the proper way of writing integrals. So now we have, on the left side, we can move out the negative 1 over rc because it is a constant. And then over on the right-hand side, we're left with this here. Simply just integrating it down, we end up here. Pretty simple. Not much to it. And now we can actually get the right values that we need for this equation. Now over here, we simply have the fact that this equation here will end up generally giving something a little bit like this, although typically the discharge rate, say we're up here at say 32 or something like that, it's going to drop a little bit faster than this, typically, and then come out and keep on going. And if I were to show you the value over here, this is actually 0.0625 or something right around there, if I remember right. And it never really goes to 0, as it keeps on going out, but it never truly hits 0. Although after a certain amount of time, you can basically call it 0 because the charge is not worth anything at that point. And that is basically the entire use of this equation. And of course, you have to have the constants related to each of the items that you're working with.